Welcome to the fourth module in our In a Nutshell series on pulmonary equations. In this module, we're going to talk about the Bohr equation and the Venous-Admixture equation because they're really two sides of the same general idea. And in this talk, what we're going to develop is the idea that the Bohr equation, which is about physiological dead space, tells us about the fraction of minute ventilation or airflow that's not very useful for getting rid of carbon dioxide, whereas the Venous-Admixture equation, or physiological shunt, is an equation that tells us about the proportion of cardiac output or pulmonary blood flow that's not very useful for picking up oxygen and carrying it to tissues. And the bottom line of this in a nutshell module really is that lung disease through VQ mismatching causes inefficiencies in both air exchange and blood flow, such that both the physiological dead space and the physiological venous admixture are going to be increased. So looking first at the efficiency of airspace, what we see is that some of the air we take in goes to the gas exchange surfaces where it picks up carbon dioxide and during the subsequent expiration carries it back out into the atmosphere. On the other hand, some of the air we take in goes into the physiological dead space where it doesn't meet the gas exchange surfaces, comes into contact with no blood flow. And so when it comes back out, it has just as little CO2 as it had when it went in. And we can recognize that alveolar ventilation and dead space ventilation, when added together, make up the total ventilation, which we call minute ventilation, or V dot E. And the idea here is that all the CO2 comes from the alveoli, from the alveolar ventilation. And therefore, we can say that the alveolar ventilation times the fraction of it, this CO2, must equal to minute ventilation times the fraction of it, which is CO2. With just a few little changes, we can say, well, alveolar ventilation, the total amount going to the gas exchange surfaces, is the total, the minute ventilation, minus the stuff that doesn't go to the gas exchange surfaces. So we make that substitution. And then we can multiply both sides by barometric pressure, and we get this equation here, which with a little bit of algebraic manipulation turns into the Bohr equation. PaCO2 minus mixed expired CO2 over PaCO2. And it tells us the ratio of each tidal breath that is wasted in the form of air just entering the physiological dead space and coming back out again. And the other thing we've done here is we've turned P little a CO2 into, or added it to this equation instead of P big A CO2, because the arterial CO2 and the alveolar CO2 are virtually the same. So the other thing that you can learn if you look carefully at this equation is this ratio here also expresses the ratio of dead space ventilation to minute ventilation, because we can multiply anything upstairs and downstairs by respiratory frequency. And what we see sometimes when you look at this equation, and we'll come back to this in a minute when we look at the shunt equation, that there is no term for inspired CO2 here because inspired CO2 is virtually zero. But let's look at the construction of this equation. The biggest value of CO2, 40 in the arterial blood, minus mixed expired CO2, biggest minus middle, over biggest, so these match, these terms match, minus little. And so the lowest CO2 is this zero in inspired air, is the way this ratio comes out. And what we learn if we put in normal values is about 30% of each tidal breath, or about 30% of minute ventilation, are wasted. So now let's talk about blood flow efficiency. So we're talking about now, instead of airflow, blood coming through here. And we notice that some of the blood flow goes through and comes into contact with the gas exchange surfaces, and some of the blood, which we call venous admixture, bypasses the gas exchange surfaces, either due to being anatomical right-to-left shunt or being ventilation perfusion mismatching. So venous admixture is just another term for physiological shunt, if you will. And so we see there's two components. There's the component of blood flow or cardiac output that goes to the gas exchange surfaces, and by the time it gets to the end of the gas exchange surfaces, it has an arterial content, which is end-capillary oxygen content, Cc'(O2). And we can use the ideal alveolar air equation to sort of figure this out with an oxygen dissociation curve. The other blood flow goes through this channel that never sees the air. And so it comes in with a venous oxygen content and goes back out with a venous oxygen content and mixes in with the freshly oxygenated blood from here and makes it a little worse. So that at the end of the day, the oxygen coming out here in the cardiac output has an oxygen content which is slightly less oxygenated than it was at the end of the pulmonary capillary, because we dumped this virtually deoxygenated blood into it. So we can sort of set this up in an equation and say total oxygen is equal to alveolar oxygen plus leftover oxygen coming from the veins. And when you mix them together, you get sort of an average which is slightly deteriorated from here. The only other thing we have to recognize is that the amount that goes to the gas exchange surfaces is the total minus the amount that went through here. So we can just substitute this in here. And again, with algebraic manipulation, you get the venous admixture equation. And what you see is this is a ratio of physiological shunt, or venous admixture, to cardiac output. And so when we look at the terms, it's biggest minus middle, this is the middle oxygen, over biggest minus little, this is the lowest oxygen. So we get a content minus arterial content, the biggest content minus venous content. And when we put in normal values for these, we find out about 6% of the oxygen, the cardiac output, is wasted due to physiological dead space, either from anatomical sources or due to ventilation perfusion mismatching. So these two equations telling us about mixed airflow and mixed blood flow are two sides of the coin about respiratory efficiency. Where this becomes important to us is in pulmonary disease, when we get increases in ventilation perfusion mismatching. And that increase in ventilation perfusion mismatching causes both an increase in physiological dead space, as would be measured by the Bohr equation, and physiological shunt, or venous admixture, as would be measured by the venous admixture equation. And these inefficiencies in airflow and blood flow are really what causes ventilation perfusion mismatching to contribute to the deoxygenation that we see in respiratory failure during lung disease. So that's the venous admixture equation and the Bohr equation in a nutshell. Thank you for watching.